There's a bunch of different VLA models you can use to move your robot, but wondering which one is the best choice for you? My name is Grigory, and in that video I will show how did I try to run 3 different VLA models, not always with success, quite old ARC, medium-aged SmolVLA and quite new Pi 0.5, and compare them across different parameters, as success rate of task execution, required GPU memory and time of reaction. Additionally, at the end of the video I will have a little bonus for you. I also tested the Pi 0 model and compared it with other models as well. Which model performed the best? Why one of them, no matter what, completely refused to work for me, while reducing frame per second parameter in one particular case actually improved the quality of inference. And does the bigger model always means the better one? Welcome! Okay, so our first test will be quite simple. We'll use the ARC, SmolVLA and Pi 0.5 models to check how they will perform in simple pick-and-place task. First thing I need to do is to record a dataset of about 50 episodes of our pick-and-place. Ready? Let's go! Finally, I managed to record my dataset. There have been many problems when I tried to set up that recording. Constantly there have been some complications with USB port names, with camera setup, with some disappearing calibration files for the arms. But finally the dataset is here, and now we can go and train our policy for our rubber duck pick-and-place dataset. So let's run both training nodes on the remote GPU and on my local machine. Let's start from remote GPU, where we need to run our Pi 0.5 training. To run a training of Pi 0.5, we need to copy a command from the LeRobot official documentation about training it. There is that command, I just copied it in my notebook, and let's start training. In meanwhile, we will also start training of our ACT policy. Okay, both training started. I see in weights and biases, our training still proceeds. And it's almost finished. The loss function, as we can see, going down. My ACT policy is trained already. Let's also train the SmolVLA policy on the same dataset on my local machine. My training just crashed 2400 steps over 3000. So training crashed just because funds in my account. Always something happens when you have online GPUs. I many times heard an opinion that nowadays it has no sense to buy your own GPU. It's just enough to rent when needed cloud one, choose appropriate GPU, pay a few dollars for training, and voila! After a few hours you have your model ready to use. In fact, they've been my 7th GPU on which I finally managed to train my model. There've been always some problem with them. Or the PyTorch version been not compatible with GPU version, or all my files after the training is done been disappeared because I reserved not enough the disk space on the cloud machine. Or training been stopped in the middle, as you can see here, because I forgot to fulfill my account with enough funds. In fact, because of all the problems, the training took me not to $3, but 50. Actually, the biggest disadvantage of cloud GPU is not related to GPU itself. The biggest disadvantage of cloud machines is that you need to pay for disk space no matter if you're using it or not. Because of it, you can't just save your configuration, all downloaded files and libraries for next half of year and return to work after such time. You pay here for every day you store your files, and because of it, every time you want to train something, you need to configure all your environment, install all the libraries again and again. And I'm not saying here that cloud GPUs has no sense. I'm also using them when my local machine is just not enough. But what I want to say, that myth that cloud GPUs are completely enough for every live use case is just nonsense. Using the local machine is much more convenient. If you have funds to invest on your local GPU, just do it. I just finished training the models to control my robotic arms and also arm in the simulation. All 3 of them, ACT, SmolVLA and Pi 0.5. So now let's try to run them on the robotic arms and let's see how every of them perform. It did it! It did it! You see, I just replaced some duck manually and did again trying to place duck in appropriate place. Yes, he did it! Amazing! Well, he doesn't pick at the duck actually, but he placed it in the needed place. Okay, he decided that episode has succeeded. Let's say that been success. He managed to pick up the duck, he placing it on the appropriate point. Yes! He did it again! This is definitely not a successful episode. One more time. So, I just made a 20 episode of our ACT policy and it has 50-50 efficiency. It's 10 episodes when it succeeds and 10 episodes when it's not. Also, in my opinion, if it succeeds or not, it really depends on where we'll place our duck. So maybe if we'll have more training data and more training steps, we can improve also quality of execution and improve that success score. But still 50% it's not big. Also interesting experiment, I just reduced the action horizon from 50 actions to 20. Action horizon means how many actions our policy predicts at once. So with reduced number of steps, it also makes that flicker movements, but that movements are smaller and more frequent, has less amplitude. So in case of ACT policy, very lightweight policy, we can afford to reduce the training horizon and improve the performance of the model. Give me that. 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 Give me. Bad dogs. Okay, so now let's run our SmolVLA model and we'll see if it will be better or worse. The model downloaded. Again, instead of pick and place it, just use dragging. Let's say it succeeded. Well, that episode is half succeed. I'm not sure if treated as not succeeded or maybe succeeded. Let's just keep such episode. Give me that. Give me that. Bad dog. Well, for some reason SmolVLA don't want to release my duck at all while placing it in the good place. Okay, let's say been successful. Again, he's not releasing the duck, so let's calculate such episodes as half success. I can skip unfortunately such episodes because there's like too much of them. I just finished test of my SmolVLA. On 20 episodes I tried, 10 being the complete failure when our arm wasn't able to even pick up the duck. Another 5 being a relative success when it successfully pick up the duck and place on the appropriate place and let's say leave it. And another 5 being like half succeed I say, because in that episode our arm pick up duck successfully, placed on the appropriate place, but wasn't able to release it. I'm not sure actually how to interpret that results, if been success or not. Even if we treat them as success, we still have 50% of success rate of SmolVLA on that experiment. So exactly the same with ACT, which had like much more clear success in case of succeed episodes. And also our SmolVLA takes 2 times more GPU memory than ACT during the inference. While ACT has a little bit more than 2 GB, our SmolVLA have more than 4 GB. At least at that experiment, our ACT been clearly better than SmolVLA. Better successes with small resources used. Now it's time to check out Pi 0.5 and let's see what will happen with that model. I'm very curious because I've never tried that model before, so let's see how it performs. Let's see how that model behaves, and it behaves very strange. Because I've been waiting for like around a minute, and finally after that minute or two, robot moved and stands. And calculates next actions, and calculates them very long time. It's definitely not real time when he calculates the actions. Inference of Pi 0.5 failed. Robot just moved once and stayed forever. Honestly, I must admit that despite of following all documentation and spending many hours on trying to run that model, I haven't managed to do it. The single benefit of that experiment is that at least I measured the amount of VRAM our model requires. So here are results. ACT policy, much lightweight and less VRAM hungry, completely overbeat the much advanced SmolVLA. What about memory consumption? ACT requires little bit more than 2 GB of VRAM, SmolVLA requires little bit more than 4, and Pi 0.5 requires around 8. We will try to interfere ACT and SmolVLA with our Unity simulation, our test number 2. We'll use exactly the same simulation environment I set up in Unity in my previous video. If you're interested how to set up such environment within Unity, make sure to check out. So let's start our custom policy server. Our policy client will be Unity. Okay, this is definitely not a sensitive episode. Now policy didn't found and watermelon just made our barrel to go like somewhere endless at the sky. Okay, let's do it. Yeah, do it, baby. Almost there. I can see that ACT policy is actually trying to aim at the watermelon, but aims like just too high or at high portion of that watermelon. It does not perform shoot. I can count that episode like half of success. What's also very interesting about ACT policy that calculating actions takes for that policy extremely little of time. So every action is calculated in like 3.7 milliseconds. Other models calculate much longer. Okay, so testing of the ACT policy in the simulation of shooting the watermelon is finished. As previously with SmolVLA, we have here a lot of half-succeeded episodes. So actually for 20 episodes, we have 6 of them that been completely unsucceeded, and the rest, 14 of them, been, like I would say, half-succeed. So our gun been able to target the watermelon, but wasn't able to trigger a bullet. So if we'll count such episodes like, let's say, succeeded, our success rate will be 70%. Also, what's interesting about ACT policy's inference time is very low. It needs less than 4 milliseconds to calculate the action, which is nothing for such policy. For comparison, sending that action from the server to the Unity client takes about 20 milliseconds. Now it's the time to test our SmolVLA policy. First shot, first hit. Okay, let's start our calculation with SmolVLA, starting with one positive episode. And in exception of ACT, it's really positive episode, it's really shooting our model. It's quite unstable on that iteration. I don't know why. Okay, so I think I found the reason of that unstable movements and made something to improve that. Now our SmolVLA is quite stable after I reduced control FPS from 10 to 7. Now you can see also movement is more smooth because now it's enough time for SmolVLA between that action requests to proceed the action, calculate new action and send new action here. So reason being just too frequent updates and just our policy, our computer wasn't able to generate new actions on time. Now let's calculate our stats again. Okay, positive. There's still some instability on that movements, but well. Okay, very nice. I think we have that small instability because in some moments that calculation of action takes even longer than the standard 90 seconds. So after reducing frame rate, our SmolVLA model performed much better. It has success rate of complete shoot into the watermelon and hit it at 30%. Partial success rate, aiming at watermelon but not shooting it, is 90%. So it's much more bigger than in case of ACT, but it also has own cost. Time of calculating a single step for SmolVLA is much bigger, around 90 milliseconds. So definitely to run that model you need to have a better hardware. Okay, and now we're running P0.5 policy, which is successfully running on my simulation, but it is not able to shoot my watermelon. Like it seems the policy does not seize an watermelon at all. Also another interesting thing that the inference time of single step of that policy is about 40 to 41 milliseconds. So it's strange, but it's like 2 times less than in case of SmolVLA. So I'm really happy I managed to run the Pi 0.5 at least in simulation, but the results wasn't satisfactory. It seems like model doesn't understand, doesn't see the watermelon, so it has completely 0% success rate. At least I managed to run it and I'm quite happy with this only that single fact. The single thing I managed to know about Pi 0.5 is its inference time, which is 2 times smaller than in case of the SmolVLA, which is smallest model. The most probable reason of it, as I read on the Discord group, is because the Pi models are somehow optimized for the libraries on the top of which they run on. My summary and conclusions on the experiment number 2. This time, SmolVLA is completely overbeat the ACT model by the cost of the 20 times longer inference time. The Pi 0.5 model wasn't able to work again because of some LeRobot library bug of mismatch the model and the library inputs outputs. And I prepared little bonus for you. Been quite unsatisfied with the fact that Pi 0.5 does not started to work in both experiments, I decided to try older Pi 0 model. However, when run on a real model, I experienced exactly the same problem as with Pi 0.5. The robot just moved once and stopped. Let's try the experiment with simulation, but I guess the result will be the same. But now, see, it works! It works! It works! It works! Simulation results of Pi 0 model are comparable to SmolVLA. The success rate is exactly the same 30%. The half success rate is little bit lower. The inference time and GPU memory consumption is on the same level as in case of the Pi 0.5. As for now, we learned a lot of different model parameters, but what all the numbers actually means for us? Let's sum up them in few simple sentences. ACT is a very lightweight model. Good choice if you want to run it not on very powerful hardware, for example an edge device. SmolVLA performs sometimes better, sometimes worse than ACT, mostly better, but check out for your use case. The single thing we can say here for sure is that it requires much more resources. Some bugs in the LeRobot library prevented me from running Pi 0.5 model. I think that bugs will be resolved relatively fast, and it's very possible in the moment you're watching that video, bugs are already gone. Some people already managed to run that model and they confirm that Pi 0.5 completely overbeat all alternatives. If it's true, after bugs will be finally solved, there will be no reason at all to use the Pi 0 model, because both of the model requires exactly the same amount of resources, but Pi 0.5 is much better. If you watched that video till that moment, thank you very much for it. By watching the video till the end, you helping my small channel to grow. Also, I will appreciate if you click a like button and leave a subscription. It will again help the channel grow as well. And if you have any questions or problems appear during running your models, feel free to ask them in the commentaries. I can't promise I can solve all your problems, but for sure I'll read all the comments and will try to help. And last but not least, please share your opinion. If you like me to produce more deep dive programming tutorial like this one, when we coding or training models, or you want me to show more hardware videos like previous one, when we assembled our robot, screwing all the screws, printing details and so on. By the way, if you're interested in the LeRobot project and want to see how it been assembled, I think that previous video is the interesting material for you to watch. And this is actually all from my side for today. Thank you for watching again and see you next time. Bye.